We are now going to discuss bipartite graphs. So bipartite graph is a graph that can be divided into two parts in some sense. So let me show you an example on the screen here. So consider the graph that you see on the left. If I move the vertices around a bit, I can make it look like the graph on the upper right. Notice I have put A and C on one side and B, D, and E on the other side. In particular, observe that I can color the left-hand side green and the right-hand side blue in such a way that edges never stay on the same side or never share color on both ends. This relates to a question called the two-coloring problem as well. You have the graph. You would like to color the vertices in such a way that adjacent vertices never have the same color. And this graph, I can use the same green and blue coloring from the bipartite drawing to give a proper two coloring. So here's our definition of a bipartite graph. A graph with vertex set V and edge set E is bipartite if the vertex set can be split into two parts, V1 and V2. These are called a partition, such that edges do not connect elements of the same partition. So you can see that in the upper drawing here, where the edges only go between the left and right side. So here are a few examples we can look at. So let's ask whether any of these are bipartite. So start with the graph on the left. I want to try to draw this so that all the edges go between the left and right side. And one way you can do this is pick a starting point. A high degree vertex is often a good starting point, but in this case, they're all the same. So I will take the vertex A and put that on the left. Then look at its edges and draw the other ends on the opposite side. So B and D. Now continue like that. The next point is C. From B and D, I need to go back to the other side again. And this has used up all the points and all the edges. And so that shows us that this is bipartite. The way it was drawn before, I put two colors, green on the left, perhaps blue on the right. So this also could have been done as a two coloring. B and D get blue, A and C get green. So either you can two color it like you see at the top, or you can draw the bipartite version. I would suggest the bipartite drawing because the two coloring is not always immediately understood to mean the same. Let's look at the second graph. I'll follow the same approach. Start with A on the left, and then connect it to its neighbors. So A goes to B and to E. Now from B, I need to connect back to the other side again. So from B, I go to C. From E, I go to D. And then C and D are connected. Notice that as I constructed this, I never had a choice in what I did. If I had a choice in how I alternated back and forth, it is possible I would fail like this, and it would be my own fault. But in this case, once I locked A into the left side, I was forced to put B and E on the other side, and then forced to put C and D on the left. So when we look at this and notice that I ended up with adjacent points colored green, this tells me it is not bipartite. Again, it is essential that I had no choice along the way. Anytime I make a choice, I potentially mess it up. Now let's look at 3. Follow the same approach. A goes on the left. It doesn't have to be A. In fact, why don't we do B this time? I mentioned that high degree vertices are a good starting point. So if B goes on the left, then A, E, and C are forced to be on the other side. Why are they forced to be on the other side? Because they're next to B. And a bipartition, the partition must put all the neighbors of B on the opposite side of it. Now we run into a problem because A and E are next to each other. And so looking at the blue side of the figure here, there are two adjacent vertices. So again, this is not bipartite. Whenever you claim that something is not true, you need to justify it. And one of the ways is to explain the construction. You could say starting at A, let's say on question 2, you are forced to alternate this way. Question 3, you could say starting at B, you are forced to put A, E, and C on the other side. Okay, here's an alternate approach though. If you studied graph colorings, you will have learned that there are a couple of special cases. One of them is if you have a complete subgraph, then you must use at least that many colors. In particular here, I have these points A, B, and E, and together they make a complete subgraph on 3 points. That means you must use a minimum of 3 colors. That's a problem because we're trying to 2-color it. So one explanation here, which is not start at B and move to the other side, is the graph contains a K3. The graph contains a K3, A, B, E, and so the chromatic number is at least 3. If you don't know about graph colorings, that's fine, but if you know about graph colorings, this is another way to show that you need more than 2 colors, and so it is not bipartite. Looking at question 2, there's a similar thing. There are 2 standard cases for colorings. One is complete subgraphs, another is odd cycles. So this has C5 as a subgraph. That means we have 5 points in a ring. In fact, that's the entire graph here. And if you have an odd length cycle, you need at least 3 colors. If that odd length was 11, it would still be 3. Whereas on the right side, if we had K4, we would have 4 colors. So these are 2 different ways to show that something is not bipartite. What you can't do is say, I tried and failed. It's not bipartite. So always justify your answers.